I'm Mark Rennies, host of Euler's Melting Pot, the challenge where we try to complete every Project Euler problem in a different programming language. But today, we're going to talk about something a bit different. A friend of mine recently published an interesting puzzle game called Constellat 10, and it has some interesting mathematical properties that I'd like to discuss. Constellat 10 is a game made for the GMC Jam 56 by Alice. This is what a level of Constellat 10 looks like. We have several lights arranged in an arbitrary shape, and each light has a symbol on it. Some of the lights are initially on, while others are initially off. We can click on any of the lights. If we click on any of the lights that has a plus icon, it toggles itself as well as any lights vertically or horizontally adjacent. If we click on one of the lights that has an X or times icon, it toggles itself and any lights diagonally adjacent. The later levels add a few more types of lights with different shapes, but we'll talk about those in a bit. The goal of a level is to either turn all of the lights on or turn all of the lights off. On each level, it's up to us to determine which way the lights need to go. If we find ourselves stuck, there's a time-released hint system that reveals the state of one of the lights, to help us move forward with the correct solution. But today, we're going to be working out the mathematics behind this puzzle, so we won't be using that feature. When we want to start thinking of a puzzle game in a mathematical sense, the first thing we need to do is identify what sort of mathematics we're going to do on it. I want to eventually write a computer program that takes the state of a puzzle board and produces instructions to the player, telling them where to click in order to solve the puzzle. For the purposes of this puzzle, where to click simply means which light to click. For instance, we could imagine assigning each light a label, and then a list of instructions might proceed as click light C, then light F, then light B. This gives us a starting point. A list of instructions, naively, is a monoid. A monoid is a set on which we define a binary operation that is associative and has an identity. Our set is the set of possible lists of instructions. The binary operation is concatenation. That is, if one instruction says click C, and another says click F, then we obtain a composite instruction that performs those two clicks in sequence. This operation is associative. That simply means that parentheses are irrelevant. If I have three instructions and I want to compose them in a specific order, it doesn't matter if I compose the last two or the first two first. We also have an identity, though it looks a bit silly. The identity instruction is do nothing, which we can write with a lowercase e for empty. To minimize the possibility of confusion, I won't label any lights with the letter E. So if I write a lowercase e, I'm referring to the identity element, which means do nothing. Now, our particular monoid has quite a bit more structure than we've given it credit for so far. For one thing, every action we can take is reversible. This isn't the case in arbitrary puzzle games, but it is the case here. If we click somewhere and decide we've made a mistake, we can always undo the action. A monoid where every element is invertible is called a group. And in our group, the way to reverse an action is simply to do it again. That is, the inverse of any group element in our group is itself. That tells us we're working in a Boolean group. Boolean groups have several interesting properties. The first immediate property is that if we have two elements of our Boolean group, we can perform them in either order. To see this, let x and y be arbitrary elements of our Boolean group. Then the inverse of the composite term xy is xy, since every element is its own inverse by assumption. But the inverse is also yx, as we can see directly. The term xy can't have two inverses, so these two must be equal. That is, xy equals yx for every x and y in the group. In most areas of mathematics, we use the word commutative to describe the property that we can switch the order of arguments to a binary operator, but group theorists felt the need to be different, so we call a group with this property an abelian group. Stepping back to our original problem, this tells us that the order in which we click the lights doesn't matter. So rather than giving instructions as an ordered list, click C, then click F, then click G, for example, we give them simply as an unordered collection, click C, F, and G. Alternatively, we can just assert without loss of generality that we will always provide the lights the player should click in alphabetical order. Now that we know our group is abelian, I'm going to start writing the group composition operator with a plus sign rather than the dot or simple juxtaposition. So if x and y are two arbitrary instructions to the player, I'll write x plus y to be their composite. Likewise, I'll identify the identity element, which we were previously calling lowercase e, with 0. The fact that our group is abelian tells us that x plus y equals y plus x, as any well-behaved addition operation should be. The fact that our group is additionally a Boolean group tells us that x equals minus x for all x in the group. This means that, in the context we're working in today, plus signs and minus signs are the same thing. Now, let's trivialize the problem for a moment. Instead of several lights, let's imagine we just have one light. In an extremely boring, simple puzzle involving just one light, there are only two things I can possibly instruct the player to do. I can either say, do nothing, which we designate as 0, or I can say, click the only available light, which I'll designate as 1. And clicking the light twice is the same as doing nothing, hence 1 plus 1 equals 0. This completely describes the one-light puzzle group. In fact, we already have a name for this group. It's the group of integers modulo 2, written as z modulo 2. And if we have multiple lights, the multiple light group is just the direct product of several copies of this. So the relevant group for a puzzle involving n lights is z modulo 2 to the n. I'd like to emphasize that, so far, we've only discussed how to instruct the player on what they should do. We haven't discussed the net result of those player actions on the puzzle state. That is, as of right now, all n-light puzzles are equivalent, and the relative positions and icons on the lights don't matter. In any case, we're working in the same group of instructions. But now we're going to talk about how that group affects the layout of the puzzle. The current state of a puzzle is a tuple or list of zeros and ones telling us which lights are on and which lights are off. Note that although these are zeros and ones just like our previous light clicking group, these values mean something different. In the group we just made, a value of 1 indicates that the player should click on the given light. In this new set of states that I'm about to build, a value of 1 indicates that the light is currently powered on. A player clicking on one light will affect multiple lights, and a given light is affected by multiple possible player clicks. So on the one hand, we have the group of player actions, denoted as z modulo 2 to the n. On the other hand, we have the set of puzzle states, which we can write as s to the n, where s is a two-element set 0, 1. If I have an initial puzzle state, and I give the player some instructions, those instructions are capable of acting on the puzzle state to produce a new puzzle state. So our z modulo 2 to the n group can act on the set of puzzle states in the form of a group action. No, that's actually what it's called. A group action of a group G on a set S is a function from G cross S to S, which respects the group identity and composition operations. Concretely for our puzzle problem, this means that the trivial do-nothing instruction should not modify the puzzle state, and that performing two instructions in order should have the same net effect as performing their composition. If these sound like trivial constraints when I phrase it like that, then great. That means you're getting the hang of it. As a reminder, the goal of the puzzle is, given an initial set of lights, to click some of them such that either all of the lights are on or all of the lights are off. We now have the tools to rephrase this in terms of group theory. The goal of the puzzle is, given an initial state element of s to the n, find an element of our group, z modulo 2 to the n, which takes the initial state to either the state of all zeros or the state of all ones. Which is great. We've taken a simple, fun puzzle game and turned it into a dense word salad of mathematical jargon. Mission accomplished. Of course, the ideal is that we can now use that dense word salad of mathematical jargon to actually do something useful. Let's see what other patterns we can identify. Strap in, because this is going to get rather abstract and potentially a bit philosophical for a minute. There's something special about the group z modulo 2. It's not just a Boolean group under addition modulo 2. We can also meaningfully multiply elements of this group. It's a bit silly and trivial to celebrate the fact that we can multiply the numbers 0 and 1 together, but bear with me here. In fact, let's get a bit sillier and more trivial. Not only can we multiply numbers in this group, but we can also divide by all of the non-zero elements in this group. That is, we can divide by 1. It doesn't do very much, but it is something we can do. A group in which we can also multiply and divide, subject to some basic coherence conditions, is called a field. So the group z modulo 2 can actually be extended into the field that we conventionally call F2. Now, if you took any math or engineering classes in college, you almost certainly encountered linear algebra, the study of matrices and vectors. And you learned how to do operations over matrices, how to solve matrices, how to factor them, and a bunch of other things you've almost certainly forgotten since then. But what they don't tell you in a first-year class on the topic is that you can do all of linear algebra, not just over the real numbers, but over any field. For example, the same tricks work on the complex numbers, since we can add, subtract, multiply, and divide. And indeed, the same tricks work over F2. Put another way, everything you learned in linear algebra can be done just as well if we're in a universe of only zeros and ones. With this in mind, we can view our instructions to the player not as a tuple of zeros and ones, but as an n-dimensional vector, where n is the total number of lights in the puzzle. And similarly, we can view the collection of lights that are currently powered on as an n-dimensional vector. Both of our sets now have the shape of the vector space f2 to the n. We have two vector spaces. They look identical, but we're treating them as distinct since they have distinct semantic meaning to our problem space. It sure would be nice to be able to convert a player instruction vector into a light state vector. Converting from one vector space to another is done via a linear transformation, more concretely realized as a matrix. And a linear transformation is completely specified by its action on a basis of the domain vector space. If you aren't currently holding a degree in mathematics in your hand, you probably started to zone out somewhere during that monologue. Let me show you what I mean. Let's work with this very simple puzzle configuration. We have 4 lights, so all of our vectors are going to be 4-dimensional. We'll label these lights as A, B, C, and D. As a quick visualization, if I were to click on light A in this example, that would toggle lights A and B. Clicking on light C similarly toggles lights B and C. Clicking on B toggles all 4 lights. And finally, clicking on D toggles A, C, and D, but not B. Note that in this particular puzzle, and indeed in any puzzle containing only the plus and times symbols, clicking on a light always toggles itself, potentially in addition to other lights. This won't always be true. The later puzzles contain some other shapes that don't exhibit this behavior. But fortunately, that won't affect our calculations in the slightest. Now, let's write these actions as vectors. If I click on light A, it affects lights A and B, but not C and D. So the vector representing that action is 1, 1, 0, 0. If I click on light B, it affects all 4 lights, so the vector for that action is all 1s. Light C affects B and C, but not A and D, so the vector is 0, 1, 1, 0. Finally, light D affects A, C, and D, but not B, for a vector of 1, 0, 1, 1. Now we have 4 vectors. If you imagine these vectors becoming good friends and hanging out close to each other, you get a 4x4 matrix. Now if I take a vector containing only a single 1 and zeros everywhere else, and I multiply it by this matrix, then I recover one of the columns. Remember that the vector we're multiplying by is the vector of player instructions. So a vector with a 1 in, say, the second position and zeros everywhere else corresponds concretely to the instruction, click on light B and no others. In this case, the net effect on the game board is the second column of our transformation matrix. But this analogy extends. If I have a more complicated player instruction vector, I still get the net effect of the composite of all of those actions on the puzzle state. Let's consider the player instruction click B and C. This corresponds to an input vector of 0, 1, 1, 0. Now we multiply the matrix and the vector. Keep in mind we're still fundamentally working over the field F2, so all addition and multiplication operations are implicitly modulo 2. The result vector is 1, 0, 0, 1, which tells us that if we click on the lights B and C, we'll toggle the states of lights A and D, but not the states of light B and C. All of this is to say, once we have the transformation matrix built for a particular puzzle, we can view the net effect of any player actions on that puzzle as matrix multiplication. In fact, in this particular case, we can say a bit more. This transformation matrix is invertible. That means it has full rank, which means the columns are linearly independent and span the vector space. Put another way, regardless of starting configuration, in this puzzle I can get to any puzzle state I want to if I know the right lights to hit. There are no unreachable puzzle states. This isn't true in general. For example, this simple 2-light puzzle is not a full rank matrix. Both of these lights affect each other, so if the puzzle starts with all lights off, there's no way to turn one on without the other. In any starting configuration, there are always 2 achievable light states and 2 unreachable ones. Now, the goal of the game is to either turn all of the lights on or turn all of the lights off. The developer of the game, Alice, has assured me that every puzzle in the game can only reach one of those 2 states. That is, in a given puzzle, it's possible to either turn all of the lights off or to turn them all on, but not both. Phrased slightly differently, if we're in the all lights are off state, it's impossible to reach the all lights are on state. Thus, all of the puzzles in this game are singular matrices, which is a fancy way of saying non-invertible. Let's follow this tangent one step further. An n-light puzzle has, a priori, 2 to the n possible states. If the transformation matrix for the puzzle is full rank or invertible, all of these states are reachable. However, consider the case where the matrix is not invertible. The collection of reachable states is a vector subspace of our original 2 to the n vector space, and a vector subspace is still a vector space, which means it has a dimension. So the set of reachable states must have cardinality 2 to the k for some k smaller than n. This also tells us that every state which is reachable can be reached in 2 to the n minus k ways. Alice told me every puzzle in this game is singular, and she's pretty smart, so I trust her. Therefore, every puzzle in this game has at least 2 ways to get to the proper solution. It might have more, and in fact, the number of ways to get to the solution is always going to be a positive power of 2. So, at least for all of the puzzles appearing in this game, the solution we will end up finding is not unique. With that fun little tangent out of the way, let's talk about how we're actually going to solve this thing. Let's assume we have a puzzle, and we've already calculated the transformation matrix for it, which we'll call capital M. We also have the original state of the lights in the puzzle, which we'll call V0. For the sake of notational convenience, I'll write the constant 0 vector containing all zeros as a 0 with an arrow over the top, and likewise for the vector of all 1s. If we want to get from this state V0 to the state of all zeros, where all of the lights are off, we want a player action that produces the transition 0 minus V0. And if you'll recall from a few minutes ago, one of the beautifully fun things about working over the field F2 is that subtraction and addition are the same thing, so 0 minus V0 is just V0. Similarly, if we want to get to the state of all 1s, we want a transition that produces 1 minus V0, which is again equivalent to 1 plus V0. So we want a vector of player actions U that solves one of these 2 equations. One of these 2 equations is, per the guarantee set forth by Alice, unsolvable, and the other is guaranteed to have multiple solutions. Now, thinking back once again to your wonderful freshman-level linear algebra class, we learned a technique called Gaussian elimination, or row reduction, for solving matrix equations. Basically, if you have an equation like the one we have now, there are 3 things you can do to it that don't affect the solution space of the equation. We call these 3 things elementary row operations. The first and simplest elementary row operation is to swap 2 rows. Swapping 2 rows in the input and output of an equation does not change the set of possible multiplicand vectors, which can solve the equation. The second operation is to multiply an entire row, again in both the input matrix and output vector, by a non-zero value. The third operation is to take one row, possibly multiply it by a non-zero value, and then add the result to another row. The great thing about elementary row operations is that they're the same over any field. You almost certainly learned about them in the context of the real number field, or possibly the complex numbers if your professor was particularly sadistic. But we can also do Gaussian elimination over the field f2. And in f2, there's only one non-zero number, and it's the number 1. So these operations are quite a lot simpler. In our domain, the first operation, swapping rows, is unchanged. The second is completely eliminated. There's no sense in ever multiplying by a non-zero number if the only non-zero number that exists is our multiplicative identity. And the third is merely add one row to another. Again, there's no sense in pre-multiplying if there's nothing reasonable to multiply by. So our two operations for the rest of this problem space are swap rows and add one row to another. The goal of Gaussian elimination is to convert the input matrix into the identity matrix. If we start with mu equals some vector w, and we manage to, by some application of elementary row operations, convert m to the identity, we're left with u equals some vector. That is, we've just solved the equation for u. Let's see an example. We'll go back to our previous example with 4 simple lights. Let's say the lights B and D begin in the on position, and I want to turn all lights off. Then the equation we want to solve is m times u equals 0, 1, 0, 1. For notational convenience, we write the relevant values we'll be manipulating as an augmented matrix. Really just a matrix with a line in the middle distinguishing the inputs from the outputs. So our augmented matrix is this. Now we want to convert the left-hand side to upper triangular. That is, I want 1s on the diagonal whenever possible, and everything below the diagonal to be 0. It will be possible in this case to have a full diagonal of 1s, since the matrix is invertible, but it won't be possible in general. Looking at the first row, I already have a 1 in the diagonal position, so I'm going to add the first row to the second row. Now my first column looks good. It consists of a 1 in the diagonal and zeros all below it. Let's take a look at the second row and column. The second diagonal is a 0, not a 1, so I'm going to swap the second and third rows to put a 1 in there. Now I want to get rid of any of the 1s below the pivot position, which is on the diagonal. Currently, that's the fourth row, which still has a 1 in it, so I'm going to add the second row to the fourth row. Keep in mind, we're doing all addition, multiplication, and really any operations modulo 2. So when I have 1 plus 1, that equals 0. Now we're looking at the third row and column. The third diagonal is already a 1, but there's a 1 below it, so I'm going to add the third row to the fourth row to eliminate it. And now we have an upper triangular matrix. We have 1s along the diagonal and zeros below it. Now that we have an upper triangular matrix, we get rid of any 1 values not on the diagonal, so we wind up with the identity matrix. So I'm going to take the fourth row and add it to all of the above rows to eliminate this entire fourth column of 1s. Now I'm going to add the third row to the second one to eliminate the 1 above it. And finally, I've got one more 1 not on the main diagonal, and I'll eliminate it by adding the second row to the first row. In the end, once we see the identity matrix on the left, we get 1, 1, 1, 0 on the right. This means that if we start with B and D active, and we click A, B, and C in any order, we'll end up with no lights active. We can easily verify that this is the case. Starting with our initial puzzle state of BD, clicking on A leaves A and D on. Then clicking on B toggles all lights and leaves us in state BC. Finally, clicking on C disables the 2 remaining lights, leaving us with 0 lights active. Since the transformation matrix was invertible, this solution is unique. No other sequence of user inputs would solve this puzzle, except for obviously trivial modifications like hitting the same light twice in a row. Let's see another example, this time one that isn't invertible. This is another 4-light puzzle, this time arranged in a parallelogram shape. In this case, it's actually pretty straightforward to see that not every puzzle state is reachable. Every light affects 2 lights, including itself. So anytime we click something, we'll toggle exactly 2 lights. If we start in a state with 0 lights on, we can reach states with 0, 2, or 4 lights on, but there's no way to end up with an odd number of lights powered on. Nonetheless, let's solve this just like we did before. Light A affects lights A and C when clicked. Light B affects lights A and B. C affects C and D. And finally, D affects B and D. This is our transformation matrix. Now let's say we're in state 1, 0, 0, 1. That is, lights A and D are on, and B and C are off. And we want to turn all of the lights on. Our desired transition is 1 minus 1, 0, 0, 1, or 0, 1, 1, 0. So the equation we want to solve is our transformation matrix times sum u equals 0, 1, 1, 0. Let's try to row reduce this as much as possible. First, I want to try to get to some upper triangular form. I add the first row to the third to eliminate the 1 in the first column. Then I add the second row to the third to eliminate the 1 in the third column of the second row. Finally, I want to get rid of the 1 at the bottom of the third column, so I add the third row to the fourth row. Unfortunately, I can't find a pivot for the fourth row. It's all zeros, and I have nothing to swap it with. The most we can get on our main diagonal is 3 1s. However we do it, we'll end up with an entire row of zeros at the bottom. Now, if the row at the bottom had been zeros with a 1 at the end, that would indicate a contradiction. That is, that would tell us that our equation is not solvable. Since it's all zeros, that tells us that we have multiple solutions. Now, let's back substitute again. It's not a perfect algorithm since we don't have an invertible matrix, but we can do the best we can. At minimum, we can knock out the 1 in the second column at the top. And what we're left with is as close to the identity matrix as we can get. Lights A, B, and C appear neatly on the main diagonal, but light D does not. This tells us that, with the way we've currently solved this equation, D is a free variable. That is, we can set the fourth element of our vector, which represents light D, to either 0 or 1. That then determines the other 3 values. There's nothing special about light D. We could have solved this in a different order and gotten a different free variable. But for us, right now in this moment, it's light D. If light D is 0, which means we don't click on light D, then we can read the rest of our solution in that context. That effectively eliminates the fourth column of our augmented matrix. If light D is 0, then C is 0, B is 1, and A is 1. So one possible solution is 1, 1, 0, 0, corresponding to the player clicking lights A and B. Starting from the puzzle state with A and D on, clicking A moves us to state CD, and clicking B leads us to the desired state with all lights on. We can also assume light D is 1. In that case, we have to do a bit more work to our augmented matrix. Since light D is 1 by assumption now, we can subtract that column. Yes, we're subtracting columns now, not rows, over to the right-hand side of the augmented matrix. Now the right-hand side is 0, 0, 1. The bottom element doesn't matter because it's just all zeros. So that tells us that if we're determined to click on D, then we should also click on C and leave A and B alone. Starting again from the AD state, clicking C gives us AC, and D moves us to the desired ABCD state. We had one free variable D, and we tried every possible state for it, so this gives us all the possible solutions. The only 2 ways to get from light state AD to the light state with all of them lit is to either click on AB or to click on CD. Now, to be clear, these are small example matrices. The very first puzzle in the real game has 19 lights. That's a 19 by 19 transformation matrix consisting of 361 values. If you want to go build and subsequently row reduce that matrix, be my guest, but I have better things to do with my time. So instead, we're going to write a computer program to do it for us. In fact, we're going to make it as easy as possible for our hypothetical user. Specifically, this is the input format I want to target. We're going to read 2-dimensional grids from an input file. The first tells us the shapes and positions of the buttons, and the second tells us which buttons are on and which buttons are off to start off with. Let's do this in Python. Python's NumPy library has some good matrix capabilities and even a function to do the row reduction, at least the first half, for us. We're going to use the Galois package, which extends the well-known NumPy package to work over finite fields, including F2. The rest of these imports are unexciting. Some data classes, Python system package, and a healthy dose of static typing imports. Now we tell the Galois library that we're working over the finite field F2. This creates a class which we'll locally call GF, of matrices with elements in F2. When added, subtracted, or multiplied, all operations on this class will implicitly happen in the field F2. Now we write a class for 2-dimensional coordinates in a grid. We could just use a tuple for this, but I want to be able to add and subtract these. Next, a class for 2-dimensional grids. This is a big one, and I'll be the first to confess I stole some of this code from an older project of mine. A 2D grid has a width, a height, and the actual data stored as a list of lists. And we provide a handful of helper, getters, and setters for fields using the position class as the index type. Next, we write some higher-order helpers for mapping over grids with an arbitrary function, as well as for pretty printing the resulting grid. I'm moving quickly because a lot of this is just Python niceties, and not strictly related to our problem domain. For example, we write several class methods that act as alternative constructors for our grid, and a way to convert back to a list of lists. Alright, next we'll write the class that contains the single instance of the puzzle. The puzzle data consists of a grid of lights, stored as a grid of one-character string values representing the shapes, and a grid of initial states. Puzzle data objects can be initialized directly using the data class provided initializer function, but we'll also provide a helper for reading them from a file in the format I just invented. Finally, we'll provide some simple delegators to get the puzzle width and height from the grid. Finally, we write a very simple class to represent a solution to our puzzle. A solution is a list of booleans indicating which lights to press, and just for fun, we'll also include the number of free variables we have so we know how many total solutions there are. Now I'm going to program in all of the adjacency rules for the different shapes. We discussed the plus and times shapes, but this game actually has a few more shapes it uses in later stages. The plus shape affects itself and anything directly adjacent to it, but excludes diagonals. The times shape affects itself and anything diagonally adjacent to it. The box shape, which I'll denote using a capital B because I don't have a box on my keyboard, affects the 8 lights immediately around it, but not itself. The circle shape, which I'll denote with a lowercase o, affects 12 lights in a larger circle around the current one. A horizontal equal sign, which I'll indicate with a dash, affects the whole row, including itself. Since this is Python and not Haskell, lists have to be finite, so I'll just include 100 positions in each direction and hope the puzzles are never larger than a 100 by 100 grid. Likewise, a vertical bar affects a whole column of lights, including itself. Finally, a hash sign affects both the row and the column. If you haven't written Python in a bit, you may be slightly shocked to see a switch case statement, which was frequently lamented as a missing feature in Python for several years. As of Python 3.10, not only do we have a switch case statement in the form of the match keyword, it's actually a pretty general purpose pattern matching tool as well. In any event, in case of an invalid button type, we'll simply error out. Next, we'll write a few small helper functions. One to construct a grid from the next few lines of a file, one for adding vectors of booleans to the field f2, and one to convert a grid of booleans into a matrix in f2. Now we get to the meat of the problem. Let's move back up to our puzzle data class and finish writing it. We need to build up to a set of functions that will build our transformation matrix. First, we write a function that produces, as an iterator, a sequence of all of the positions that contain a light, as opposed to simply containing empty space. To that end, we iterate over all indices in our grid, and yield only the ones that are non-empty. This function is more important than it looks at first glance. We're producing all of the lights in order. This is actually how we're going to label our lights. In the handwritten examples we did earlier, we used capital letters to label the lights. In this program, we're going to use the two-dimensional grid coordinates. On top of that, the order of the lights produced by this generator method is going to correspond to the order of lights in our matrix and vector representations. So the relevant position function, despite how simple it looks, serves as a source of truth for a lot of the puzzle's logic. To make that more explicit, we write a function called positionsMap that produces a mapping from the position labels to the index in a vector. This can be done with a simple dictionary comprehension. Now we provide the initial state as a vector. The initial state is an ordered list of booleans, in the order of our relevant positions generator, indicating which lights begin the puzzle on and which lights begin the puzzle off. For convenience, we also provide similar helper functions that produce our two goal states, the state of all ones and the state of all zeros. Finally, we'll write a function that I'll call vector4. This is a bit of a complicated one. Given a label, that is, given a position, of a light, I want the column vector indicating its effect on the puzzle state. That is, if we're analyzing the light at position P, I want a 1 at every vector index that the light at position P changes, and a 0 at any position it does not. To build that vector, first we get our positions map, which maps from position labels to indices in the vector. Then we identify, via the adjacency function we wrote earlier, which positions in the grid are affected by this light. Keep in mind that not all of these positions actually contain lights, so we need to do a quick filter operation to narrow it down to the ones we care about. Once we have that, build a vector of all zeros, then iterate over the affected positions and update those values to 1s. Finally, return the vector. Now we have all of the tools we need to build our transformation matrix. Inside our main block of code, we read the puzzle data. Then we double check that the two grids have the same dimensions. I actually added this check later. After mistyping the grids about 20 times, I got fed up and told Python to yell at me when I messed it up. Once we've verified the puzzle dimensions are correct and our sanity is intact, the transformation matrix is simply all of the column vectors we just built, concatenated together in order. So iterate over all the lights in the puzzle in order. For each light, produce the column vector indicating its action on the puzzle, and concatenate. Next, we need to be able to row reduce these things. The Galois library gives us part of this puzzle. If the matrix was invertible, we could leverage the Galois library to directly invert it. But all of the matrices we care about today are singular, so we have to do a bit more work. The row reduce function takes the transformation matrix as a grid of booleans, as well as the desired result transformation vector, and produces a solution, or the Python Sentinel value none if no solution exists. Let's get started. We let n be the number of lights in our puzzle, which is also the height of our input matrix. Next, we build our augmented matrix, which consists of the original transformation matrix with one extra column added for the output. There's a bit of NumPy magic happening here to reshape everything into the right dimension, but nothing crazy. Now we tell the Galois library to row reduce the augmented matrix. This gives us an upper triangular matrix with as many ones on the main diagonal as possible. When we worked through these examples by hand, I said we have to check any of the all zero rows at the bottom. If there's an all zero row with a 0 at the end, that means there's a free variable. But if there's an all zero row with a 1 at the end, that's a contradiction and there's no solution. So for each row in our row reduced matrix, check if all but the last column is 0. If so, check the value of the last column. If the last column is 0, we found one more free variable. If it's 1, we found a contradiction and we can bail out immediately. If we reach the end without bailing, we know there's at least one solution. To keep things simple, I assume all of the free variables are 0. I can assume whatever I want about the free variables since they're free. And keeping them all 0 just seems the simplest way to write this function. Produce our result values array. It's initially all zeros, except that I'm throwing an extra 1 at the very end. This represents the output state during back substitution and effectively just allows the desired outcome to have an effect on the variable values. Think of it as just mathematical paperwork. For each row in the matrix, starting from the bottom, find the pivot. That is, find the first non-zero value. Ideally, this will be on the main diagonal, but not always. If there's no pivot, then we're looking at a free variable row of all zeros and can skip it. By the way, for loops in Python support an optional else block. A lot of people have never used that before. If a for loop has an else section, the else block gets run when the loop terminates normally, but not if the loop exits early due to a break or return statement. Once we have our pivot, update the value of the pivot based on the known values of the variables to the right. Finally, produce our solution structure, consisting of the values we built up, as well as the count of free variables. We omit the final element of the values array, which again was just a formal pseudo-variable to allow the desired outcome to have an effect on our back substitution. Now let's pretty up the output a bit. Once we have a solution, if it's deemed impossible by our magic row reduction function, we print impossible and return early. Otherwise, print a nice pretty grid in the same format as our input. And just for fun, print the total number of solutions as well. And at last, we put it all together. We have our input matrix. First, we try to reach a state where all of the lights are on. To do this, we subtract the desired state, with all ones, from the initial state, keeping in mind that subtraction and addition are the same because I said so. Then we row reduce to get to the output state, and pretty print the result. Do the same thing for the nothing state of all zeros, and that's it. Once again, this is the first level of the game. This is what it looks like in our input file, and when we feed this into our clever little Python program, we get some nice, pretty output. There are 4 ways to get to nothing, with this being one of them, and there's no way to get to the all state in this particular puzzle. This same approach can be used to solve all of the puzzles in the game, and this solves Constellat 10 in Python. Next month, we'll be back on our usual schedule with Project Euler problem number 32 in COBOL. See you guys then.